fine chemist. Someone told me they needed me to re-record this, so I am going to record one just for you, Sarah, and make this available. So here we go. You already know that K, I gotta get the right pen thing here, K equals the ratio of products over reactants. Okay, I assume you're smiling and nodding at home. So K equals that. And that is, K stands for constant. It means some number. 42 is what the K value stands for. It is some constant reaction. This tells us this reaction favors products, that the product molecules are more stable than the reactant molecules are because K is greater than 1. Smile and nod. That's been fairly qualitative so far. Now we're going to get to do a little more mathy math. Here we go. So let's write down this reaction. Write it down. You don't need to write down the aqueous things. That just tells you, of course, as you've learned, that you get to include these in the equilibrium expressions. Their concentration does change. They are a variable. Spread them out a little bit when you're writing this. These are going to become columns that we are going to work under as we go through this problem. This is a very classic type of AP chemistry problem. It is called an ice problem for reasons that will become apparent in just a second. See that word ice coming initially here. We're going to talk about that. If you want to title things today, icy. Getting ice. Ice problems. Ice problems. Doom, 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 doom. That's the kind of thing we're working with. Okay, so the initial concentration of this is 10. The initial amount of protons we have floating around in here is 12 molar, and the initial concentration of A minus is 30 molar. This is a kind of unlikely scenario realistically, but it makes for some easy integers for us to work with to avoid decimals as our first problem. So we've written down the reaction, we've written down these are the initial conditions. They're going to tell us some change. The amount of A minus or HA that went away was minus 3. For every one of these that I lose, I should get one of each of my products. That's what my coefficients are telling me here. So if I lose 3 of these, the change for this one is going to be plus 3, and the change for this one is going to be plus 3. Smile and nod. All right. So when I get to sweet, sweet equilibrium, the promised land, what are these ratios going to be? What are these numbers going to be? Well, the amount of this is going to be 7. Okay, you all know enough math to know this is going to be 15, and this is going to be 33. Smiling and nodding throughout the land, those make sense as numbers. Okay, so if we then think about like putting those in to an equilibrium expression, this is going to be concentration of H plus times concentration of A minus over concentration of HA. Although I should have brackets around them, but you get the idea. Okay, so we're going to put these numbers in. It's going to be, let's see, 15 times 33 over 7. I'm putting in these numbers to the equilibrium expression. The HA concentration at equilibrium is 7 molar. Now this is 15. Now this is 33. Smiling and nodding. Now we just need to do some math. If you think about it without your calculator, 15 over 7 is going to be just more than 2 because 14 over 7 is 2. So it's going to be a little bit more than 2 times 33. It's going to be something like 66 or 70. Okay? If you do it on your calculator, I think you get like 70 point something. We're going to go with 71 because of sig figs. This is your classic ice problem. They gave us some initial information. They gave us some change. We're using that to predict the change of other things to get the equilibrium amounts, putting those into our friendly equilibrium expression, and then you've got this. Smile and nod. 3, 2, 1. Bleep. Here's a reaction with a little bit more going on in terms of coefficients. Okay, we have H2B. 2B or not 2B, okay? Making 2 H pluses and a B2 minus. Smile and nod, write that down. Here are your initial conditions, 10, 20, and 30. Here is your change. In this case, we're talking about the product. This product grew by 2. If we think about the coefficients here, this has a coefficient of 1 or doesn't have a coefficient. For every one of these that is made after you've lost one of these, that's going to be -2. How about this one? That's got a coefficient of 2. For every one of these that gets made, 2 of these guys get made. So if I'm making 2 B minuses, I must be making +4 for the H pluses, for the free protons. So when I get down to equilibrium, this is going to become 32. This is going to become 14. And this is going to become 18. Okay? My equilibrium expression for this puppy is going to be the ratio of products over reactants. For this one, it is going to be this monster. Okay? H plus squared over B2 minus, times B2 minus over to H2B. And this one is squared, these one are just 1, because this is our next sort of warm-up level problem. We're now going to put these numbers in, okay? I'll get a pen going on here. So this is going to be 18, this one is going to be 14 that we're going to have to square, and this one's going to be 32. And if I put those in and start doing calculator math, 14 squared times 32 over 18, you can think 14 squared is going to be a little less than 15 squared. 15 squared is 225. So this is going to be around 200. This is going to be like 2. 32 over 18 is close to 32 over 16. So this should be around 400 as a guesstimate. When you actually plug and chug, if you're in the free response part of your AP exam, you'll have your calculator and you can calculate it as 348. But we wanted to guess the order of magnitude first. We only have 2 sig figs, really, so we'll report this as 350. And yes, if you want to be detailed about it, these are going to be those should be decimals to make it 2 sig figs. But whatever, you got the idea of how to do the problems. Smiling and nodding throughout the land. All right, got a new problem here. Giving you just coefficients of 1, so you know it's not going to be too bad. Initial conditions, write this stuff down. Nothing in the change row. Dun, dun, dun. But don't worry, my friends. Instead, they're giving us an amount at equilibrium. We can go back and look at this one particular spot and figure out what the change must be. Okay? If it was 10 and now it's 6, the change must have been -4. Okay? If that one was -4, because this is the simplest of these, this is just going to be +4, this is going to be +4. When I get to sweet, sweet equilibrium, this one's going to be 16, this one's 34. And the rest, my friends, is algebra. Okay? It's just computation. It's just plugging and chugging. Our K value is going to equal 16 times 34 over 6. Let's see. 34 divided by 6 is approximately 6, a little bit less than 6. And because 36 divided by 6 is 6, and that times 16 is 96. So this is going to be like 90-ish. Let's go ahead and plug and chug. 16 times 34 divided by 6 is 91, if we pay attention to sig figs, which we always do in Dave Soul's classes. Okay, smiling and nodding. Okay, in this case, it was a little different. Instead of giving us the change, they gave us the equilibrium, but you guys are smart enough to be able to put that together and deal with things. 3, 2, 1. Okay, here we go. Initial conditions for the combustion of water, hydrogen and oxygen, not combustion of water, combustion to form water, hydrogen and oxygen making water. We got 2 coefficients. We're going to have some squarage happening here. Initial conditions, no change. There's what it is at equilibrium. I'm going to give you some time to think about this, and I will come back once you've worked on this problem. So we can look here and say this went down by 6. If that went down by 6 and has a coefficient of 2, this one must have gone down by 3. Think about that for a sec, okay, because that's 2 to 1. This one must have gone up by 6. 12 minus 3 is 9, slightly harder but doable. 456 plus 6 is going to be 462. Okay, our equilibrium expression, let's see, for our K value for this thing, it's going to be H2O squared in the numerator, H2O squared over H2 squared times O2. Okay, and we have got what these all are at equilibrium. So it's just a matter of putting those in and plugging and chugging with the calculator. 462 squared divided by 16 times 9. This is what calculators are for. 1482. If we probably want to be honest about our sig figs, we're going to have to say like 1.5. Probably going to have 2 sig figs. 1.5 times 10 to the third. Because we probably have 2 sig figs in this. We could say 1500. But why not look fancy in science and say that? Okay, questions on that move? Solving for the change from the equilibrium amount. Oh boy. Here, now that we know how to do the pieces, let's do it on a actually pretty hard piece of chemistry. So here is your chemical equation. Step 1, balance that chemical equation. Okay? And then we'll get step 2, doing an ice problem. But let me let you feel some strength in what you can do and go ahead and do some balancing there at home, Sarah. And if you want to call a friend as you're working on these, you potentially can, to make sure that your balancing makes sense. So I'm going to get my cursor thing. I'm going to do the big reveal. Hopefully that is what you got when you balance. It's a little tough because you had the non-integer number of oxygens, the 3.5 oxygens that requires to double everything through the reaction. We've already taught balancing. We don't need to go back to that. So now we've got all of our proper coefficients and we've got our initial conditions. So let's go ahead and we're going to do a different line here. I'm going to say change x, change in terms of x. This just means like what are the coefficients? For this it's going to be, get a pen, -2. Right? Every time the reaction goes, for every one reaction, I lose 2 of these. Am I going to gain or lose oxygens? For every time the reaction goes, I'm going to lose 7 oxygens for every x of reactions. This is going to be plus 6x, and this is going to be plus 4x. Smile and nodding? Cool. Now let's see what the change they actually give us is. This is -4. So from that, you should be able to fill in what these other pieces are going to be. Okay, what is the x going to have to be? Well, the x is going to have to be x equals 2, because -2x ended up being -4. So this is -2. From that, you should be able to fill in what these other pieces are going to be. Zoom. -14 plus 12 and plus 8. Smile and nod that those are our changes. Now it should be pretty easy to find out what our equilibrium amounts are going to be. This was 5 minus 4. 212 minus 14. Okay, fortunately, I have these already written down. but we can do all this math. 700 plus 12 is, 712. Like, you guys can do that stuff. Okay? Now it's a matter of putting them into a much more beastie, gnarly equilibrium expression. Our equilibrium expression is H2O to its coefficient, to the 6th power, CO2 to the 4th power, C2H6 squared, and O2 to the 7th. So we got lots of math we get to do here. To get an initial guess on this thing, I would treat these as powers of 10. This is 1. This is like 100-ish as a power of 10. So just in terms of thinking about what our answer should be in the neighborhood of, which is what you often have to do on the multiple choice problems, this is 10 to the 3rd, 1,000. 712 is pretty close to 1,000. I mean, it's less than that, but if we had to guess, what the K value is going to be in a multiple choice, and it didn't give us a calculator, we might look at something like this, okay? So this, we then would raise the power to the power, means we multiply 10 to the 18th times 10 to the 12th, the 1 goes away over 10 to the 14th. This is going to be 10 to the 30th divided by 10 to the 14th, so it's going to be less than 10 to the 16th. Okay, why less than? Because we were really rounding up by going from 600 to 1,000. So it's less than 10 to the 16th is what we could conclude. If we actually do all the math, which you should do since you have a calculator there at home, since you have a calculator there at home, you should plug this in, 712 to the 6th power, 608 to the 4th power, that should give you 1.3 times 10 to the 17th, and 1.37 times 10 to the 11th. Okay, then you are going to take the denominator, 198 to the 7th power, and you're going to get something like this. Okay, and then I think that I bothered calculating all that out, so I did not. If I remember correctly, it is, in this case, the exponent, which is all that really matters, is 10 to the 12th. I believe the number portion is 1.5. So I think your final answer is 1.5 times 10 to the 12th. That is some good old-fashioned plugging and chugging. All right. Put your pencils down for a second, as they see in SAT testimony. We're just going to think about this next problem. You are not going to be expected to do this level of problem yet, but there's a preview of the sort of stuff we are going to do. K is a constant, so you often don't have to figure out the K unless it's like a reaction nobody's ever done before. The combustion of hydrogen, people have seen that before. It has a K value that's very far towards like the product side. Okay, it has a very big K. Water does not spontaneously turn into hydrogen gas. Hydrogen gas burns in oxygen like the Hindenburg blimp explosion. Here is again, you're just watching this reaction. Here is initial condition. There's a little bit of hydrogen around. Let's say there's no oxygen, a little bit of water in gaseous form. Assume everybody's gaseous, so they're including the equilibrium expression. We know that the change is X. Because there's 0 hydrogen, some of these maybe are going to go back. Don't worry about the physical aspects of it. Just think about like what the equations are saying for right now. If that is X, this is going to be minus 2X. And this is going to be plus 2X. Smile and nod. So when I get to sweet equilibrium, this is going to be 1 plus 2X. This is going to be X. And this is going to be 45 minus 2X. I know that all that ratio equals 1.4 times 10 to the 8th. Here's my equilibrium expression. H2O concentration squared over H2 concentration squared times O2. This stuff, if I plug these in here, it's going to equal 1.4 times 10 to the minus 8. And here is me doing that. Okay? 45 minus 2x, 1 plus 2x squared times x. All of that equals numerically 1.4 times 10 to the 8th. Now, you could, if you didn't have anything else to do with your young lives, solve that. You could, using some calculator tricks or doing a lot of like foiling, you could generate this, you could divide, you could get some solutions, one will be rational, one will be irrational, and you could like get to your answer. We don't want to do that math. No thank you. No math. No math. No algebra of that level of difficulty. We have a better solution here. And the better solution that we have, the chemistry solution, is the fact that this equilibrium favors the products. It's way heavier towards products. We're going to end up with a lot more of this. X is going to be small because we're not going to have very much of this reaction happening. It's so small that it's probably going to be like 0.00007. And to the measure of sig figs that we have for this, that doesn't matter anymore. It just goes away. So we're going to rely on the fact that we know chemistry enough to say that this 1.4 times 10 to the 8th is more going to essentially equal, going to approximately equal 45 times 1 squared, and these are both squared, times x. Because compared to 45, this minus 2x isn't going to be measurable. Remember, this exponent is 10 to the 8th up here. It's way going to be products. There's going to be almost no reactants. So x is going to be so small that we can say that this ugly, horrible math, we can, thanks to sig figs, hallelujah, like you didn't think sig figs were going to make your life easier. Here they make your life so much easier because to the degree that we can measure it, this x is going to be infinitesimal. It's going to be like removing a hair from your head, and you don't have to worry about it. So you can assume that it's something like this, and then that's a really easy piece of math to do. You're welcome, okay? That is what you are going to be doing tomorrow. This was a little preview thereof. I hope you've enjoyed it.